Hi everyone, welcome back again to Mathematics for Engineering 3. Today is going to be about homogeneous equations, right? The homogeneous systems. The third case where all the roots are complex numbers. Okay, so we're going to be looking at the case where the roots are complex numbers. Okay, so let's start. Uh, Well, the method is pretty much the same as the previous one. First, we need to solve the characteristic equation, which is the determinant of a minus mi equals 0. So basically, we subtract m to the diagonal line, and then we find the determinant, and then we let that be 0. After that, we get the eigenvalue, right? Let's say we get one eigenvalue, which is m1. Okay, and it's a complex number. It's a complex number. Let's call it alpha plus beta I. Okay, alpha plus beta I. So this alpha is called the real part, and this beta is called the imaginary part. Right, it's the real part and the imaginary part. After that, we need to find the eigenvector k1. Okay, which is in this form, which is u plus vi. Okay, so the eigenvalue m1, which is a complex number, gives the eigenvector, which is a complex which is a vector of complex numbers as well. Okay, so we need to make sure that we are on the same page. m1, which is a complex number, give k1, which is in the complex form as well. Okay, u and v, they are vector. Okay, they are vectors. Okay, and if you have m2, m2 is the alpha minus beta I. And if m1 is an eigen value, it means that if m1 satisfies this equation, m2 satisfies that equation as well, because it's the conjugate of m1. Okay, and k2, which takes this form, is the eigenvector as well. Okay, but in practice, we don't care. Okay, it's a engineering course, so we are more interested in producing solutions. Okay, we're not interested much in the theory. Okay, so the solutions x1 and x2 are in this form. Okay, so this case is extremely easy. Okay, it's very easy if if you can remember this formula. Okay, so basically once you get mi, okay, then you find ki. After that, you obtain the solution, which is in this form. Okay, so let's look at an example. For example, this one, find the general solution for this equation. So first, we need to find uh, m, right? We need to find m, or eigenvalues, using the characteristic equation. So we have that 2 minus m minus 5, 2 minus 4 minus m equals 0. So we have 2 minus m minus 4 minus m plus 10 equals 0. Okay, that's the determinant. I think all of you already know how to compute the determinant. So here is minus 8, and then here is plus 4, here is minus 2, so it is plus 2m, and then plus m squared plus 10 equals 0. So we have m squared plus 2m plus 2 equals 0. Okay, and then you try to factorize this guy, and you see m, and you can see that you can't really find numbers here, right, to make this true. So in that case, we need to use the formula. Okay, the formula, if you remember, is x equals minus b plus minus square root b square minus 4ac divided by 4a. Okay, and right now our a is 1, our b is 2, and our c is 2. So here we have m equals minus 2 plus minus square root 4 minus 4. A is 1, b is 2, divided by 4. So we have that m equals minus 2 plus minus square root minus 4 divided by 4. And that is minus 2 plus minus 2i divided by 2. So we have minus 1 plus minus I. Okay, and you can just take m1 equals minus 1 plus I. Okay, and you just ignore the other m. Okay, you just ignore the other m, because the other m, which is the 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 conjugate, is already included in this formula. Okay, so you just need to take one of them. Okay, you have 2m, right? You have 1 plus I and 1 minus I. You just take one of them and call that m1, and you just forget the other one because it's already included in this formula. It's already included in that formula. Okay, cool. Next, when we have m1, right, which is minus 1 plus I, so we need to find k1. Okay, and to find the k1, we look at a minus m1 I k equals 0. So we have 2 minus 1 plus I, minus 5, 2, and minus 4 minus 1 plus I. And then we have k1, k2 equals 0. Okay, so here is going to be 3 minus I, minus 5, 2, and minus 3, minus 3 minus I. And that is k1, k2 equals 0. Okay, so we obtain this equation, which is 3 minus I k1 minus 5 k2 equals 0, and 2 k1 minus 3 minus I, let's say plus minus 3 minus I k2 equals 0. Then we need to write k2 in terms of k1. So we have that from here, we have that 5k2 is actually 3 minus I k1, which means that k2 is actually 3 minus I divided by 5 k1. Okay, that is 3 minus 1 divided by 5 k1. So my big k1 would be k1 and 3 minus 5 divided by 3 minus I divided by 5 k1. Okay, so if we pick k1 5, we have that our big k1 here is 5 and then 3 minus I. Okay, and then we can split that to real part and imaginary part. Okay, so the real part would be 5 and 3. The imaginary part would be 1 0 and minus 1 I. Okay, and we call this vector u, and we call this v. Okay, because if you don't forget here, k1 here is u plus vi. Okay, so let me remind you, our lm1 is, what is it, minus 1 plus I, which means that it is actually the same as minus 1 plus 1i, right? Which means that the alpha is minus 1 and beta is 1. Okay, so we can get, the solution using the formula. So the first formula would be e to the alpha t. That would be e to the minus t. And then we have u cos beta t minus v sine beta t. So we have u, which is 5,3 cos beta t, which is cos 1t, minus v, which is 0 minus 1 sine beta t, which is sine t. And then we have x2, and that is e to the alpha t as well, which is e to the minus t. And then we have v cos beta t plus u sine beta t. So that is going to be 0 minus 1 cos beta t plus u, which is 5,3 sine beta t. Okay, and that is our two solutions. So our general solution is c1 x1 plus c2 x2, and that is c1 e to the minus t 5,3 cos t minus 0 minus 1 sine t plus c2 e to the minus t, and then we have 0 minus 1 cos t plus 5,3 sine t, and and that is our solution. Okay, so let me just wrap it up here. First, we find the eigenvalue m as usual, right? We use this characteristic equation. After that, when we obtain this equation, we need to solve for m, right? And you figure out that you can't really factorize it, so you need to use this formula to get, the root m, and it's going to be the complex numbers. And then you just take one of them, let's say m1 equals minus 1 plus I. After that, you take this equation, which is the one that we have used many times, right? And then we obtain this system of linear equations in k1 and k2. After that, we write k2 in terms of k1. Okay, so from here I have that 5k2 is 3 minus I k1, which means that k2 is actually 3 minus I over 5 k1. And in that case, we have the big k1 like this, and then we just substitute k1 with 5, and this cancel out, so we have this as a vector k1. After that, we need to split this k1 in the real part. This is called real part and imaginary part, which are u and v. Okay, and don't forget that our m1 is this guy, which means that alpha is minus 1 and beta is 1. Okay, and we use, this formula to obtain x1, x2 solutions. Okay, after that, the general solution is just the linear combination of x1 and x2. and that's it. Sorry guys, there's a typo here. uh Here the formula is actually minus b plus minus square root b squared minus 4ac divided by 2a, not 4a. Sorry, is divided by 2a. So here is 2a, and here is 2. Okay, and here is 2 as well, and here is already correct. Okay, it's a typo, sorry. Okay, next example. This one, we just, first we need to find the eigenvalues m, right? So first I'll look at the characteristic equation. So I get 1 minus m, 0, 0, 2, 1 minus m, minus 2, 3, 2, 1 minus m equals 0. Okay, and then I find the determinant, which is 1 minus m cubed, and then I have plus 0 plus 0 plus 0, and then plus 4 1 minus m equals 0. So I pull 1 minus m out, so I get 1 minus m squared plus 4 equals 0. So I get 1 minus m, 1 minus 2m plus m squared plus 4 equals 0, which is 1 minus m, and then m squared minus 2m plus 5 equals 0. Okay, so now we can apply the formula, which is x equals square root b, x equals minus b plus minus square root b square minus 4ac divided by 2a, right? So we have minus b, which is 2, plus minus square root b squared minus 4ac divided by 2b. 2a, sorry. So it's 2 plus minus square root minus 16 divided by 2. And that is 2 plus minus 4i divided by 2. Which means that our m is 1 plus minus 2i. Okay, so right now we know that our m is 1 from here, this one, m is 1, and 1 plus minus 2i. Okay, so we have two m's, which is 1 and 1 plus minus 2i. How about we begin with, for m equals 1, and this is back to the distinct root case, right? We want to find k1. Okay, let's call this m1. Okay, so we look at the a minus mik, right, equals 0. So we have the matrix 0 0 0 2 0 minus 2 and 3 2 0. Okay, basically we take this m as 1. Okay, so this is 0, this is 0, this is 0, so we get 0 to this side, and the rest are the same. And then we get k1, k2, k3 equals 0 0 0, and which means that we have 2k1 minus 2k3 is 0, and 3k1 plus 2k2 is 0, and we need to write down k2 and k3 in terms of k1. Okay, so from here we have that k3 is actually the same as k1, and from here we have that 2k2 is actually minus 3k1, which means that k2 is actually minus 3 half k1. In that case, we have that k1, the big k1 is actually k1, and k2 is minus 3 half k1, right? And then here we have k1 as well. Okay, so we have k1 minus 3 half k1 and k1. Okay, so how about we choose k1 equals 2. Okay, So we have that the big K1 would be 2 minus 3 and 2. Okay, that's 2 minus 3 and 2. And our x1 would be 2 minus 3 to e to the 1t, okay, which is e to the t. Good. After that, we look at the case, we have m equals 1 plus minus 2i, right? So I only take m as equals 1 plus 2i. Okay, I take m as 1 plus 2i. For m equals 1 minus 2i is going to be included in x1, x2 automatically. Okay, so I only need to take one of them. You can take 1 minus 2i if you want, but I like the positive number. Okay, so I take 1 plus 2i. Okay, actually I shouldn't say positive because 1 plus 2i, we don't actually know whether or not it's positive or negative. But anyway, I'll take the plus sign. Okay, so I look at a minus m, let's call this m2, m2i k2 equals 0. Okay, so we have that the a is 1 0 0, so we get 1 minus 1 plus 2i 0 0, and then we get 2 1 minus 1 plus 2i, and then we have minus 2. After that we get what is it, 3 2 and 1 minus 1 plus 2i, and then we have k1 k2 k3 equals 0 0 and 0. Okay, after that here it would be minus 2i 0 0 to minus 2i, and then minus 2 and 3 2 and minus 2i, and then we get k1 k2 k3 equals 0 0 and 0. Okay, after that we get that minus 2i k1 equals 0, 2k1 minus 2i k2 minus 2k3 equals 0, and 3k1 plus 2k2 minus 2i k3 equals 0. Okay, we obtain these three equations. But from here, from the first equation, we know that k1 is actually 0. Okay, so this k1 is 0, this k1 is 0. Okay, which means that here we can solve for k2 and k3, right? We can solve for k2 and k3. So here, from the first equation, we know that okay, how about I take this equation? I know that 2k2 is actually 2i k3, which means that k2 is actually ik3. Okay, k2 is actually ik3. Good, good. So our vector k2 would be, what is it, 0, right? k1 is 0, k2 is k2 is I k3, and then you have k3 here. Okay, you can write k3 in terms of k2 as well. It's up to you. You can write k2 in terms of k3 or k3 in terms of k2. It's up to you. Okay, after that I choose k3 equals 1. So here it would be 1i and 1, which means that it can be written as 1 0 1 plus 0 1 0 I, and this is the vector u and this is the vector v. Okay, and don't forget our m2 is 1 plus 2i, which means that the alpha is 1 and the beta is 2. Okay, So our first solution, x1, would be, what is it? If you go back to the formula, e to the alpha t u cos beta t minus v sine beta t. Okay, so we get e to the alpha t, e to the alpha t, which is e to the t, right? Alpha is 1, e to the alpha t, and then we get u, which is 1, 0, 1. Okay, 1, 0, 1. Cos beta t. Cos beta t would be cos 2t. Okay, 1, 0, 1 cos, oops, sorry. Here it need to be 0 I 1, which means that this is going to be 0. Okay, so the u would be 0, 0, 1. Okay, cos beta t, and then is minus, right? Minus v sine beta t, right here, minus v sine beta t. So we need to minus v 0, 1, 0 sine beta t, which is sine 2t. After that, we get x2, which is e to the alpha t again. And then we have v, which is 0, 1, 0. Cos alpha t, cos beta t, sorry, plus u, which is 0, 0, 1. And then sine beta t. Okay. Okay. And after that, okay, sorry guys, I should write this is x2 and x3 because x1 has already been taken by this, right? So if you begin with m2, you should call it x2 and x3. Okay, so your general solution would be c1 x1 plus c2 x2 plus c3 x3, which is c1, and x1 would be 2 minus 3 2, and then e to the t, 2 minus 3 2 e to the 3, and then plus c2, and then x2, which is e to the t, 0 0 1 cos 2t minus 0 1 0 sine 2t. Okay, and after that you plus c3 e to the t, and then you get 0 1 0. Okay, 0 1 0 cos 2t plus 0 0 1 sine 2t, and that is the solution. Okay, okay, so let me wrap it up again. First, we take this characteristic equation. You should be really familiar with it, right? Because it's the same for all the cases, right? It's the same for all the distinct roots, the repeated roots, part 1, part 2, and it's the same for the complex roots as well. Okay, after that, you need to solve this equation, right? You realize that, okay, you can't factorize it. If you want, if you don't remember this formula, okay, you can use perfect squared here. You can take m squared minus 2m plus 1, right? And then plus 4, and you take perfect squared here. It might even be easier than this, okay? But if you do remember the formula, just use it. And then we obtain, the eigenvalues, 3 of them. 1, 1 plus 2i, and 1 minus 2i. And I begin with the distinct root, which is 1. Okay, and that is back to the first case, right? When we get 1m and you get 1k and you get the solution, right? You write k2 and k3 in terms of k1, right? After that, I look at the complex root. There are 2 complex roots, right? 1 plus 2i and 1 minus 2i, but they are conjugate of each other. Okay, so you just need to take one of them. Okay, and you already obtained two solutions. Okay, the other one, the other solution is already included in one of these solutions. Okay, so you take 1 plus 2i, you subtract it to the diagonal line, you get k1, k2, and k3. Okay, and then you write down this k in the real part and the complex part, right? The imaginary part. Okay, and you call that u and v. After that, you obtain the solutions using the formulas, and then you get the general solution. Okay, and that's it. And that's it, guys, for the complex roots. Okay, in the next video we're going to be looking at the non-homogeneous equations, right? And we're gonna look at the case when the vector b is not 0, and we're gonna see how to solve it. Okay, and we need to use the variation of parameters method, if you remember, in the chapter 2. Okay, see you in the next video, guys. Bye bye.